Welcome to our webinar Boston Engineering is hosting today. It's Simulation for Design for Manufacturing. It's a 20-minute presentation that we'll be doing, and we have two experts speaking to you today that I'd like to introduce. But first, my name is Victoria Nesson. I'll be the moderator today. At the end of our 20 minutes, we will have a Q&A. So if you have any questions along the way, please enter it into the Q&A section at the bottom of the screen, right down in the middle at the bottom. Let me introduce to you our presenters, Mike Marcoux, who is Boston Engineering's Department Manager and Mechanical Engineer, and Jim Shaw, our Director of Simulation. Jim, would you like to get us started?
Absolutely. Thanks, Victoria. Today, we're going to be talking on a couple things, mainly the intersection of simulation and the role it's playing with what we call DFM. We're probably familiar with that, hopefully, or design for manufacturing. I'm going to kick it off a little bit with a couple of just sort of baseline sort of understandings and a couple slides. Mike's going to take that and apply it to a couple of case studies that he's worked on firsthand in the industrial automation case. We're going to see a couple of robots, for lack of a better word, right, Mike? And then I'm going to dig in from there and talk about and show actually hands-on what a deep dive application for simulation in DFM might look like. We're going to do some of the latest generative top opt and applications for additive and sort of more traditional, say, subtractive, if you will, or plastic injection molding. So let's talk about simulation first. So hopefully you have signed up for this webinar with a baseline understanding of simulation. Hopefully you've used it before. Chances are, if you have, it's been in a more traditional application. So I kind of present here what a traditional application and a traditional set of tools might look like. So across the top, we have, again, sort of let's call it a 5-step series process, although I know R&D can be very, very messy. But if we were to distill it down to, generally speaking, a conceptual phase, a phase for design, more detailed design, a phase for prototyping, a phase for testing, and then, of course, a phase for production preparedness and production launch, and then all that other good stuff afterwards, like making money and quality control. Traditional simulation has been applied in the concept and design phases for decades now. And some of the decisions that we might make early on for design using simulation, for example, am I going to pick a plastic or a metal, or what type of alloy? So material selection, particularly a component selection. I know a lot of times, a design engineer, I've got a decision make or buy, right? Do I make something? Do I design something? Or am I going to buy something? A lot of times we might use, for example, stress analysis to say, is the part that I might buy from a supplier strong enough, or do I have to design my own? I'm also going to use it for a layout analysis or system configuration. Am I going to design an assembly that's going to be tall and skinny or short and fat? Some of the big picture type stuff, volumes and centers of gravity and things depending on the application. And then also, depending on the application, we always have to think about the environment. So if we have anyone in the audience that's from the aero or auto industry, that we have to think about shock and vibration and thermal and humidity and salt and explosive and you name it. The traditional tool set that we might use would be, of course, our language, if you will, of design, 3D CAD, a stress analysis tool, a fluid dynamics tool, and of course, anything within the electrical engineering suite, electromechanical tools like motor design, or electromagnetic like Bluetooth and radar design, high frequency. Of course, heat transfer. I don't want to forget number 5 there, heat transfer. I think that traditionally, of course, these uses of the tools, we call it compartmentalized or siloed, but traditionally there would be a stress analysis team and a fluid dynamics team and electrical engineering team, and there's not a lot of overlap. And so obviously what we're going to be talking about today is how do we avoid that, and why, and what exactly do we have at our fingertips for the new sort of age, if you will, or the current application of simulation. It really drives, in my opinion, from the DFM process, right? When we're doing design, we have to think ahead. We look ahead to the future. What would sales volumes look like? From sales volumes, I think about tooling and investment and my production volume. Am I going to go to plastic injection molding? Am I going to cut the check for that big tool, but I can get my piece part cost down? Those are the things that we think about. That is what DFM is in a nutshell. So what does simulation look like now? How are we using it when we think about the whole process, when we bring production up into our design decisions? We're going to optimize a part. We're not just going to say, oh, it has a factor of safety for stress. It's going to be optimized. The process will be optimized. Assembly processes will be optimized. Manufacturing processes will be optimized. A lot of times we simulate that, right? A stamping process, for example, right? If we're going to cut that big check for a tool for production, we want to make sure it's right. We don't want to have to do it twice. We're going to integrate components. And we see this a lot with additive right now, right? We don't want to just redesign a single part for additive. We want to take an assembly of 5 or 10 or 100 parts. Can we combine all of them together to do their job? And can we do that with a single part that is additively manufactured? So component integration is a huge thing right now, particularly in additive. And a lot of that is being driven by simulation. We're making simulation-based decisions, if you will. And when that happens, it's not just going to be a conversation at the table in the design engineering water cooler, if you will, right? It's not just mechanical. It's not just electrical. It's not just technical. It's technical, it's manufacturing, it's possibly sales and marketing, depending on your business structure, but certainly you're going to have a real business impact. You're having the conversations with the rest of the business, and that simulation's at the table. So the new tool set, if you will, or the new way that we use these tools, right? Generative topology optimization. We're going to show you an example later on after Mike shows us some case studies, okay? How can we get the perfect or most optimized geometry, the shape, the topology, if you will, to fit the needs? We're going to have algorithm-based design. That's kind of the overarching umbrella, if you will, right? How do I get to put in my constraints into the computer? How can I have the computer do the math for me and provide a solution that I could not have come up with myself, right? And I'm not going to replace a designer with a computer anytime soon, but that doesn't mean we can't work alongside them and use them for what they're good at, which is calculating. We're not just looking at electrical engineering, mechanical engineering, thermal structure, fluids. We're looking at multi-physics, electrothermal, fluid structure, interaction, okay? We want to try to think about that entire environment, all of the qualification tests, if you will, for a lack of a better word. How do we put that into the simulation process that we have up front? And then when we talk about these tools, and we'll show an example today, we have to talk about the trade-off. Do you want the answer now? Do you want the answer to be accurate within 5%? Because you have a trade-off there. I'm not saying you can't get both. In simple problems, linear problems, we can get both. But sometimes, most of the times, we're doing more complex things. That video, if you heard it in the beginning, the hard crossword puzzle, we're going after the hard crossword puzzle. We have to make a trade-off sometimes. So comprehensive use of simulation, comprehensive tool set. So before we see an example of that, we're going to have Mike jump in, and I'm going to slide over the next one. Yep. So Mike, take it away. What do we have here?
Wow, great intro, Jim, and thanks for the setup. So what we have here are two different case studies. Both of them are industrial type automation cases. One was targeted for a medium volume, the other one for very lower volume, but has a higher level of customization. So let's go into the first case study and take a look. All right, so in this case, what are we actually designing? What is this thing? So this is, think of it as a rapid prototyping system for genomes. It's taking basically all the processes that lab techs or an army of grad students would do in a sequential manner and find a way to optimize it and automate it so that you can take something that would be like maybe months of labor and distill it down into hours or days. So what are some of the challenges that we have there in getting there is, taking a look at that whole process. How do we speed it up? Where are the inefficiencies? What optimization can I do? And then how do we bring that all together in an automation platform? So what we ended up with is a system that comprised of two different 3-axis Cartesian robots with some custom end effectors. On board, we have all sorts of precision handling and transfer of fluidics. We have thermal electric heating and cooling, and a whole litany of other different things. So what we did here is, when Jim was talking previously, is we did sort of an optimization of process. So part of that is looking at all the heating and cooling. How do we kind of optimize that early in the conceptual phase to kind of set the pace for what the design is going to do? And that's where we ended up with this system is we did a lot of that upfront work. We incorporated that early in the design. A lot of the components, the make versus buy discussions were had. This was targeted towards a medium type manufacturing level, there is a chance that if it was grew in size, you might want to go back and look at other things that you could optimize, like the end effector design. It goes from how do I get that from a machine part to injection molded plastics. There are paths there. Let's take a look at the second case. So conversely, this one is at the opposite end of the spectrum. We're going to build one of these. What is this system even? So we had a client who, in the manufacturing of their product, I identified the areas where they had a high scrap rate or where errors would be occurring. They had like millions of dollars or $1 million they were losing, annually. So they decided to attack this problem by where can we get some sort of controls, where can we get some sort of checks in that are automated, that are not manual, part of an overall project to kind of automate their whole process as a goal. So what did we do? We came in and we're gonna help them design this inspection system that will take units in, test them, sort them, and then put them on an output side for operators to retrieve. So specifically, we're looking here, we have a 3-axis, actually it's 4-axis Cartesian system, three linear stages and one rotary stage, that is going to cycle these components under like an inspection system. So what's important here is also, the throughput and the takt time. That's very important. But we also are not doing sort of the broader quantity scale of manufacturing here. There's going to be one of. So what are we doing in terms of optimization? We're doing part optimization. I really want to get that cycle time down, but I also want to make sure that I'm keeping that part within the depth of field. So maybe I'm looking at those trade-offs, those classic trade-offs of weight and stiffness. How fast can I move this through here? Can I maintain that trajectory? Can I maintain that stiffness? Am I worried about things vibration and modal? All those things have to happen very early in the design process. So that's sort of like 2 separate cases in terms of quantity and type of system and the different types of simulation that kind of get baked in the early stages of each design.
Very cool. It's interesting because you look at both of those sort of side by side at first, and they look very similar, right? But once you dig into kind of what they do and why they do what they do, and then of course what went into it, 2 completely different sort of applications there. So cool, very cool. What I'd like to do now is take what Mike just showed us and put myself in the role of a designer, right? I'm going to be designing a Cartesian robot, specifically the finger on an end effector. We've got this actuator claw here with 2 fingers at the end. And as a designer, how might I, if I were working for Mike, how might I design it for 2 potentially different manufacturing processes, right? I don't know yet if I'm going to go high volume, low volume. Is it going to be a one-off? I want my design process to be identical. I'm going to anticipate, say, for example, plastic injection molding, or anticipate, for example, metal additive manufacturing. And I want to bring that into the design phase. So what I'm going to do right now is I'm going to slide over to Creo 8. Creo 8 design platform allows us to do topology optimization. So I'm going to show you an example of that and show you an example of how we might take this gripper finger, for example, and incorporate some of the manufacturing constraints into our generative top-op tool here. So on the left-hand side, we have a sort of a typical model tree you might find in any other CAD design platform. On the left-hand side, we have basically the features that we're going to be editing for a second, so I can show you how they were built. So on the first here, I've got a design criteria I call on design criteria underscore mold. That is a design criteria that's going to go into the topology optimization tool. I have a second one in parallel with that called design criteria underscore additive. Let's take a look. I'm just going to edit this for a second and look at what we've got. So on the move my video on the left hand, on the right hand side in the dialog box, what I've got here is I'm going to take the overall volume. And as you can see here, we've got the kind of grayed out shadow of what the original, maybe the CNC part might have looked like. We've got a couple of volumes that we need to keep. Those are called preserved geometries. We have to keep, for example, some bearing strength, if you will, around the pins here. And we certainly have to keep some sort of pad, if you will, whatever's going to interface with the variety of parts that this finger gripper might pick up. So I'm going to reduce that by 50%. That's one of my design goals, but I'm also going to include some of the design constraints. So for example, this one might be for molding, injection molding, right? So you can see highlighted in green right down the center, I have my draft line. It's also establishing my pull direction, which is normal to that. It's also a symmetry plane. So I'm incorporating really 3 at least different design constraints from molding. I also have set in there a draft angle, and I can add in a few others if I wanted. In this case, I'm going to target a very economical, if you will, polymer. So I'm going to go after a polypropylene, PP. And so I'm going to hopefully reduce the mass by 50%, have it meet any of the molding requirements that I want, make it cheaper, and then make it out of PP and have it still be strong enough. So let's take a look in comparison what the design criteria might look like for the additive. So in this case, I'm going to be targeting, I'm just going to go right down to the bottom here. I'm targeting the aluminum, magnesium, silicon alloy. So a typical, say, metal additive material. Because it is metal as opposed to plastic, I'm going to target a mass reduction to 25% of the original volume. Same sort of keep out or keep in regions, if you will, same starting geometry. Here, however, of course, I'm targeting a build direction as well as a critical angle. I don't want to have too much overhang, otherwise I'm going to have additional structure needed. And we'll go into exactly what it does right now. So in a typical workflow, I would hit the optimize button here, or there's also a cloud version. I can basically send it to the cloud. You can see this icon here. I would say these two probably ran somewhere around 5 to 7 minutes each. And this is a pretty typical laptop. I have 6 cores, 4 gigs of RAM. So this should be a typical design engineering laptop. If I were to send it to the cloud, it would be back down, both designs back down in about 3 minutes. So a little bit of time savings there. Obviously, part of topology optimization is to find dozens of different designs. So we might queue up dozens of different criterias and send them to the cloud. I do have, of course, the solution already loaded, which is just in the sake of time here. So let's take a peek at the additive solution. So the additive solution here, you can see, has incorporated our our build direction and our overhang. And so it has taken the material and slid it down close to where the build plate might be. This is going to reduce a lot of the supports needed. So it's going to reduce some of the post-processing time needed. It's going to reduce the print time needed. And we could say that it's pretty close, say 90% ready for printing. We might need to do a little bit of tweaks afterwards. But the good news is this is actually a full solid model. This is not just an STL. If you're familiar with the process, this is actually a watertight, what we call a BREP solid. I can come in here and do any of my CAD modeling that I would normally. I can also come in and edit some of the shape of this as well. This is all done with surface modeling. So I'm myself not a surface modeler, so I'm not going to tweak it right now. In comparison, this is the design for molding. You can see some of the features that we have. You can see our draft angle in there and our symmetry down the middle. We do have that same efficient structure, if you will, but certainly we've got a little bit more mass here. This is going to be a polypropylene, and we've only reduced the mass by 50%. But you can still, generally speaking, we have gotten our weight down, which is really, really nice. In particular, if I wanted to go to the next level, right, I'm not done. I'm not just going to ship this into production. We do have some tools inside Creo 8, for example. This tool in particular is called Live Simulation. ANSYS and PTC have a partnership which allows a lot of ANSYS technology to come in. I'm just going to hit simulate here. It's going to take about 10 seconds, but this is actually going to run a full FEA analysis, not your traditional FE analysis that we're used to, where we have to mesh it, we have to assign everything. This is all automatically built in. It's meshing it a little bit differently, and it's running it completely on the GPU, which is the graphics card. So you can see that, roughly speaking, I would say we're converged right about now, and I would say that that probably took around 10 seconds. So 10 seconds to conduct an FEA is pretty quick in the world of FEA, even for a little laptop like this. Of course, if we wanted to, and I'm going to pause that, if we wanted to, or if we needed to actually do a pre-validation, we would go right into ANSYS. So here, of course, would be a classic ANSYS mechanical and workbench, and this would be the same exact setup here, my cylindrical supports. I'm adding my load, and I'm going to look at a little bit more detail. I'm actually picking up some stress concentrations here that our quick tool, if you will, did not pick up. So full suite of tools, in this case, Creo from PTC, and also ANSYS, that are talking parametrically back and forth. So if we go back to the slides here, what just happened? So what happened was a single designer in a single environment just did two things at once. And that was shave weight, for lack of a better word, or optimize the design as a mechanical engineer might do. I've targeted 2 different materials. I've targeted 2 different manufacturing processes because I subscribe to the design for DFM process. And I've successfully used 2 different kinds of simulation. I used a quick one just to make sure I was getting the deflections I needed. And I used what we would call maybe a validation FEA, where I can get a true factor of safety. I can build in more advanced, nonlinear, if you will, dynamics, anything you would want at that point. Any of the multi-physics that we talked about earlier, that's really needed if we're going to be using DFM up front. So to recap, DFM done properly is something that we think about starting off on the first step. Project kickoff, what are we thinking? What are the constraints that we could anticipate downstream? What volumes, what processes, what materials, and how can we use simulation to make those decisions as opposed to just making them sort of qualitatively? We have a set of tools. We showed a set today where we can either do a quick conceptual or a more thorough design validation analysis. We don't necessarily want to guess here. We want to try to use quantitative tools to give us quantitative answers. And depending on where you are, concept versus detailed design, you should have a couple tools in the toolbox to make sure that it can meet the pace, if you will, of development. Mike showed, I think, 2 excellent examples where from 5 feet away, they look very similar to somebody who doesn't have as much robotics experience like myself. But when you dig deep, completely different applications, completely different, say, automation, different intended markets, intended volumes, and so different DFM constraints. And so again, in industrial automation in particular, and I hope that there's a few people in the audience that are in that industry, I'm sure you are constantly faced with either, is this a low volume, high customization where we can do additive, for example, print your name on the fly, or is this a high volume, low customization where we're looking for something a little bit more traditional like plastic injection molding? I hope that the demo showed you that there's a tool set available that your design process can be identical, even if the application is not. And that, in a nutshell, is simulation in the DFM process for industrial automation. Thank you guys so much. We didn't want to take too much of your time today. I'll hand it back to Victoria. I hope we have a couple of questions that we can go through. Thank you so much.
And you're very well. Thank you guys both for doing this. We do have a couple of questions, and we'll start off. But as we're going through the questions, anybody wants to add, we'll be more than glad to go longer than the 30 minutes. But let's start off with our first question, which is, during what part of the development process do you utilize these tools?
Ooh, that's a good one. Trick question too.
Mike, you want it?
Sure. I would say, when do you make that first design decision, and is it how is that decision informed? Could be at conception. Maybe you're doing ideation. Maybe you're getting into the other side of the down select. Early as you can.
Yeah, obviously early as you can is would be my default answer as well. But I think it's when you get to the point where you're making a decision that's either going to change the direction of the project or the design, or you get to a point where you're making a decision where you don't feel like you have enough information. And again, in product development, you never have all the information, but simulation can help fill those gaps. I would say we most often see it in the detailed design phase, right, where there's CAD already in place, but certainly it has plenty of places up in the conceptual as well when we're still trying to think of layout decisions, material decisions, and some of the early stuff. Yeah.
Great. We have another question. How do you use PLM to manage the design process in this scenario?
PLM. Okay. Somebody in the audience knows the industry. Mike, you want to go, or you want me to start?
I mean, I can give my 2 cents. I would say you need to have the appropriate life cycle set up, right, and define those ahead of time. So that's going to be part of whatever your robust QMS system is, or whatever your design process in. Hopefully that's defined at some level. Do you have a conceptual phase? What does your release date look like? A lot of this iteration is going to be done very early in that concept generation, ideation, and downsect, where you're iterating daily. So that part of it is is where I would kind of plug a lot of this into, as opposed to what Jim highlighted in some of the slides with the traditional approaches where you have a really defined CAD. Doing that on released assemblies is a little bit rough, because you're kind of, your hands are tied in terms of how do you do that change management.
Yeah, if I were to take the subset of PLM and focus on PDM for a second, which is the data management side, you create a lot of data in design, you create a lot of geometry data, you have a lot of supporting data for simulation. And I think, of course, you have gigantic results files, like, gigs and gigs, but it's the support information during the research phase and setting up for the analysis that's really important that you hold on to. It's the assumptions inside of in preparation for the analysis that you don't want to lose. That's what you want to track, because 6-12 months down the line, when a similar project comes along or a similar challenge comes along, that's what you want to go back. So from a PDM, data management, rev control, it is the data you create from the design and the data that's supporting the analysis that's sometimes more important than the analysis results themselves, because sometimes those can go on a presentation or a screenshot. Wrap that up, of course, with the whole life cycle, and the question now becomes, how much of that data are you tracking, and where and when and who's going to have that sign off? So we don't, I wish we saw more simulation as a part of the PLM process. I hate to say it, that is a dream for a lot of companies that is not realized as quickly as they think. It's quite a bit of work.
I want to just manage our time. We have 2 more questions, which we will definitely get to, so nobody in the audience will feel like they didn't have their moment. But for those of you who have to sign off at 12:30, we just want you to know that if this was a helpful webinar for you, please join us again or share it with other people in your organization. We're running it tomorrow at 4, and you can go to bostonengineering.com's website. You'll find it on our homepage or under events. And we're also offering today the opportunity to meet one-on-one with either Jim Shaw or Mike Marcoux. So if you use your smartphone to capture that QR code, it will take you right to a place where you can submit a form to schedule an appointment with either of them. And then we'll talk about some other resources we'll be offering you after our next 2 questions. So do you guys mind hanging on for a few more moments to answer these questions?
Of course.
Absolutely.
All right, we have somebody in the audience who is actually eager to get this going. And they're asking, how do I convince my boss or organization to purchase simulation software? So they're ready to go.
This is the toughest question. No. Mike, you want to start that one?
Yeah, call Jim.
Oh boy, yeah. Oh.
Yeah. How much time do you spend in iteration, in testing of breadboards and doing some of that feasibility? Is there a way that you can build that justification even before having that discussion with your boss or supervisor? Think of it that way. How much of the process can you streamline? It might be, maybe you don't have access to those metrics, but you can probably think of it in terms of hours that you spend, and then think of some cases where it might have been beneficial, and then reach out, and Jim and the team can probably take a look at, hey, this is what we can do for what you're trying to do.
Yeah, I would add just like two parts. The first is, a lot of people calculate, that's how you calculate it, right? So some people think, oh, it's an overhead, just another overhead. How do we justify that? Well, you got to look at the opportunity cost of what are you spending in right now? Mike mentioned iterations, test, capital expenses, and you name it. You have to look at sort of the big picture and say, what role can simulation play? And then what can it replace? And although you can't replace test immediately, you have to run simulation and test sort of in parallel. Ultimately, your test program will be lean, whatever that is. Maybe it means, you have partners who do some of the testing and you do some of it, or you don't have as much guesswork, and the opportunity for failure in the test is really low. That's one side of it. The other is find a quick win. Straight up, find a quick win. Maybe it's a recent pain, maybe it's a current project, maybe it's something that you're anticipating, but find a quick win, something that doesn't take a lot of investment, right? Something that you can maybe, if you needed to have a service, but find it quickly and show them that even at the small sort of immediate scale, it can show value. That will penetrate, I think, through the organization, through the conversations, and slowly but surely we'll start to see that sort of culture shift on what simulation is, which is more than just a fancy calculator.
Fantastic response and an interesting question, because we don't want this to be a fantasy. We want people to know that this is applicable. So the last question is at this same sort of how do I make sure this is a reality kind of question. And the last question we have today is, how do you trust the results? How do you know what you've run in the simulation is actually going to prove to be true physically?
Yeah, I'll hop on this real quick, and Mike, you can jump in anytime. But and I kind of just mentioned a little bit too is, I'm sure you've seen other webinars, I'll just throw it out there, that say you can replace testing with simulation. Look how we did it. And the reality is, the full story is you have to do both in parallel at the same time at first. If you're looking to deploy simulation either for the first time in your company or in a new application, i.e. a new software, a new license, a new application, you need three major things, right? Hardware, software, and knowledge. Do you have the right hardware in-house? If not, we got to get it. Do you have the right software in place? If not, you got to get it. And if you have the right knowledge in place, and there's a variety of different ways with online training that we can get that. So those are the three major pillars: hardware, software, and knowledge. And you have to run that as seriously as you ran your test program. If you take simulation and allocate the resources, and I mean the people, to that program the same as the first time way back when you first started to test something, then you're near guaranteed to find the correlation. Whether the results correlate to the test within 15, 10, 5, or 0.5% comes down a lot to the complexity of the problem, the ability to test, the ability to actually get field test data, not just bench test data. And then, of course, where the problem lies in the capability of the software. So loaded question, loaded answer. I don't know, Mike, if you've got anything to add to that.
No, I think you succinctly touched all the bases. I would say it's something that's going to change over time for you too. Initially, you might build that breadboard or prototype to test out everything that you can and validate those results in parallel. But over time, you might learn the simulation does a pretty good job with these certain aspects. I can really delve into these other areas that might be of a more concern. So then you become a little bit more focused into what you really have to kind of validate in that regard.
So this has prompted a follow-up question to that, which is, if your company isn't going to incorporate simulation software into its platform, is there a way to partner or outsource the simulation, given that it's a trial and error, or Jim, as you said, you want to do things in parallel? Is there a way to do that so that you can still use simulation to prove some points, but not have to integrate it into your company?
Yeah, absolutely. And that is, in some case, maybe even a more economical option, depending on the type of software you're looking at and the hardware required to use it, right? In those cases, if I were to say, what would you want to look for in a partner? Because, of course, most people who are in this, industry are also offering services. What you want to look for, I think, is, are you able to get the data afterwards? And many times, say we might do a service, but at the end game is for the company to get the software ultimately. But they want to go up that learning curve as fast as possible. Do a project, understand how the project was done, receive all of the native information, the native files, the design, the prep, the research, the CAD files, the FEA files, the results files, and then have that person walk you through how they did what they did. There is, in that case, I don't think any faster way to deploy it, to be honest. The learning curve is steep in many cases. I totally understand that a lot of companies would want to go up the learning curve by themselves. That's totally fine. Totally understand. There's nothing really, for many people, there's nothing better than trying it themselves. But from a speed perspective, from a calendar perspective, there really is no, I don't think, quicker way than getting the expert in, get the service done, put the fire out if this whole investigation is being driven by an issue that's hot, if you will, and then receive the data, learn what happened, and then take it from there.
Fantastic. Mike, Jim, we just want to say thank you for the great presentation today. And for those who have been able to stay on a little longer than our anticipated time, let me just tell you about a few resources that we're offering. As we mentioned earlier, the QR code on the screen will take you to a form where you can fill out information about how you want to be contacted, and Jim and Mike have offered to make themselves available for one-on-ones. We'll also be sending out the recording of today's webinar on Friday, so you can share that with your peers and colleagues. We'll also be sharing with you via email starting next week access to a resource page where we'll have white papers, case studies, articles, an overview about how to determine if your organization is ready for simulation, and again, the link to scheduling a one-on-one with Jim or Mike. So look for those in your inbox, and we want to thank everybody for participating and joining us today, and a special thank you to Jim and Mike.
Thanks so much.
Thank you very much.
Take care.